Donc
Bien.
bonjour à tout le monde. Aujourd'hui, on a Antoine Marchal pour le séminaire. Je fais l'introduction en français. Donc Antoine est actuellement à CITA, au Canada. Il avait fait sa thèse avec Marc-Antoine, Ville-des-Chênes, sur, vous pouvez le voir, milieu interstellaire et puis des méthodes d'extraction. Et je pense que c'est de ça qu'il va nous parler un petit peu aujourd'hui. Voilà. Antoine, je te laisse la parole et on va passer en anglais. Merci beaucoup.
Merci, Philippe. All right, so good evening, good morning, good afternoon, everyone. Thanks for this invitation. Really glad to be here and to have this opportunity to show you my recent work. For this presentation, I'm going to be talking about the multi-phase structure of the neutral ISM, mostly in different environments, the Milky Way disk, the Milky Way halo, and even a nearby galaxy. And we're going to see how we can extract this multi-phase structure using 21 centimeter of data. And we are going to be talking about an algorithm that I've been working on during my thesis, which is named ROHSA. Oh, ça ne marche pas. All right. So what I'm going to present is closely related to one of the main questions that is being posed by modern astrophysics, which is how do galaxies acquire the gas they need to sustain their star formation, to maintain their star formation rate. Accretion seems to be one of the key. Accretion from the intergalactic medium that is still difficult to observe because you need to be able to observe a very low column density gas around the galactic disks. And this is going to be one of the main goal of the square kilometer array to reach this very low sensitivity to observe the gas surrounding the nearby galaxies. You can also have an accretion that we can call a recycling of gas that is due to the galactic fontaine process. Basically, this is gas that is being launched from the galactic disk by supernova explosions or stellar winds. And when this gas reaches the halo, it can mix with the surrounding gas of the halo, which is a lower metallicity gas, and then just due to the gravity, the gravitational potential of the galactic disk, fall back into the disk of the galaxy to partly sustain and bring new gas to form stars. So really, accretion seems to be the key to tackle this question. But how can this gas, once accreted on large scales, cool down to form the precursors of molecular clouds? That's the question I would like to ask today, and we're going to be talking about that mostly. So we need to cool the gas. So we are talking about a thermal condensation process here, right? Because H1 needs to reach a temperature of about 100 Kelvin to allow the H1 to H2 transition to start and then form molecular clouds, and within the molecular clouds, stars. So it's a thermal condensation that is producing, that is forming the cold reservoir of neutral gas. So this is H1. So one way to study this cold gas reservoir, and it's been done extensively during the last decades, is to analyze emission absorption pairs. If you have the chance, if you can cross the path of a bright radio source in the background, typically a quasar, what you're going to see in absorption for the 21 centimeter line is basically only the cold gas that is along line of sight, because this is sensitive to the temperature. It's proportional to the density over the temperature. So if the temperature increases, you don't really see it in absorption. But in emission, you see all the gas because it's proportional to the density, only not very sensitive to the temperature. So if you do a joint Gaussian decomposition, if you analyze this and you kind of subtract the contribution of this CNM you see in absorption in the emission spectrum, at the end of the day, you can tell what's the amount of cold gas that you have along the line of sight. And you also have a very precise determination of the spin temperature, the kinetic temperature of the cold gas along the line of sight. So as I said, people have done that, and the main conclusion of this work is that there is about 30% of the gas that is in the cold neutral medium. About 50% of the gas is in the warm phase, and there is also something in between that we are used to call the UNM for unstable neutral medium, or LNM for lukewarm neutral medium. And that's interesting to see that there is something in between, and that shows us directly that the interstellar medium, the neutral ISM, but not only, is not a static medium. It's something very dynamical. You have turbulence. You have many ways to perturb the system that is a galaxy. And you have a constant circulation of gas between phases. I'm not saying that we fully understand the way the gas circulates between the phases, not only the neutral phases, but the ionized phase also, or the molecular phase. But there is definitely some dynamics that is induced, for example, by turbulence. So from a numerical point of view, people have tried to understand also the production of CNM clouds in the interstellar medium. In the late 90s, people have started to do numerical simulation of thermally B-stable turbulence. The idea is quite simple. You take a box with a fluid, low density, high temperature. So this is WNM. And you apply perturbations to mimic a turbulence. So you can have more than just a turbulence. You can have a colliding flow that produces turbulence. And then under the effect of thermal instability, the gas can, under some specific conditions, condense itself to form CNM clouds out of this very warm and diffuse medium that is the WNM. So with numerical simulation, that's really nice because you can just apply a cut in your temperature field. You can separate the CNM and the WNM from your simulation, and you can start to study the properties of each phase. Right, you can, for example, take a look at the CNM mass fraction along each line of sight, or within the entire box. You can study the turbulent velocity field, because that's what is going to trigger your density or pressure perturbations, and under the effect of thermal instability, condense the gas. Turbulence is really an important aspect here, and by nature, turbulence is multiscale. So if you want to understand this transition, if turbulence is responsible for this transition, you want to be able to analyze fully sampled maps, right? So if we want to compare numerical simulation with observations, we have to be able to do the same kind of analysis to map out the phases of the neutral ISM from fully sampled observation. We can't just do it along one line of sight, sorry, because we don't have any information about the scale, the surrounding medium around this line of sight. So that's what we are going to do today, using an observation of the 21 centimeter line in emission. You can see a PPV cube of this emission here from the Giggle survey. This is the North Ecliptic Pole observation. And if we take a closer look at a small mosaic of spectra within this cube, we can notice several things here. First of all, the signal is very complex. It's a continuous distribution of gas in here within the range -50 plus 10 kilometers per second. You have different environments, what we call the local velocity component around 0, which is the gas moving with us, with the sun, and some intermediate velocity clouds that we think is more related to the interface between the disk and the halo, so associated to the galactic fountain process. But again, on the top of that, of this complexity, we also know that it's a mixture of cold gas and warm gas. You have narrow components and broad components mixed within a single spectrum, and you don't have any information in absorption to tell you, okay, there is this amount of CNM, so I can subtract it and tell you what's the amount of WNM along the left side, along the line of sight. But we can also see that this signal varies slowly, especially. So we are going to try to use this information, and I mean, it makes sense because physically it should vary slowly, right? The physics behind is something continuous. So if you observe 20% that 20% of the mass is in the CNM along one line of sight, you can't observe or say that 90% of the mass is in the CNM right next to it. So this is why we decided to develop this Gaussian fitting algorithm that is named ROHSA. So ROHSA stands for Regularized Optimization for Hyper-Spectral Analysis. And I hope that I'm going to be able to convince you that this Gaussian fitting algorithm was designed to perform a phase separation of 21 centimeter data, but you can also use it with any kind of hyperspectral observation, because the only thing we assume behind that is a Gaussian model with some spatial coherency for the solution. So we're going to start with the data, right? It's a PPV cube that I'm going to call TB for the brightness temperature. It's a cube, so we have a velocity and we have R that is describing the spatial coordinates of this PPV cube. We can write a model. So as I said, it's a Gaussian fitting algorithm. So it's simply a sum of Gaussians here. Each Gaussian has an amplitude, A, a velocity, a position, mu, and a velocity dispersion, sigma. So first of all, and that's what we always do to fit a model on data, we write the chi-square contribution, which is just the difference between the model and the data. We divide by the noise because we want this difference to be close to the noise. We square it, we sum it, that's chi-square. And we want to find the zero of that function, such as, well, we want to find the parameters of these functions, such as Q is minimized. So we want to be as close as possible to 0. So if we do that, and only do that, as I said before, we could apply this optimization for one line of sight and the line of sight next to it. But due to the complexity of the signal, and because this is a nonlinear model, right, it's a sum of Gaussians, you have exponential in a Gaussian, there is no way you get a spatially coherent solution, the same solution. So to force that, we've decided to add what we call regularization, some energy terms that is going to penalize or to give a weight compared to this chi-square term to force the solution to be spatially coherent. So for each parameter map, we convolve the parameter map with a Laplacian kernel that you can see here. This Laplacian kernel is just going to calculate the difference for each pixel with the 4 closest neighbors. If you do that and you square it and you sum it, It's exactly the same form as the chi-square contribution, but instead of trying to minimize the difference between the model and the data, here we try to minimize the difference between the value of the amplitude of one Gaussian at this point and the value of the amplitude at this point, this point, this point, and this point. So it's really a convolution. It's a spatial filtering to penalize the small-scale fluctuations in your parameter maps. Right, so we have a spatially coherent Gaussian decomposition. But for the phase separation in H1, we need to have one more term. And this term is minimizing the variance of a velocity dispersion map. Because if you don't have any penalty related to the velocity dispersion, there is nothing that prevents the velocity dispersion map for one Gaussian to go from 1 kilometers per second to 10 kilometers per second, from one corner of the map to another corner of the map, for example. And this is a big issue because at the end of the day, you would like to be able to say, when you look at one Gaussian, one 2D Gaussian map, you would like to be able to say this is CNM, or this is WNM, or this is something in between, based on the mean velocity dispersion of this map. So by minimizing the variance of each velocity dispersion map, we force each map to be close to an unknown. This is a variable in the code, M. It's not fixed, so it's higher, but we don't ask specifically for CNM or WNM. We just ask that if there is a Gaussian and there is a velocity dispersion map, the variance of the map is minimized. So you can say this is CNM or this is WNM. So here, for example, WNM. All right, so this is the core of ROHSA. And we are going to apply that on a numerical simulation first to see what we can get from that and what we can recover assuming this model. So I'm using the same numerical simulation, the turbulence in the box by Sori et al. 2014 here, and just a part of this turbulence box. So we generate a synthetic observation, synthetic PPV cube, using also a self-absorption modeling, and we apply ROHSA on this synthetic PPV cube. So the question you may ask now is, how do I initialize the parameters of my model? We have a lot of parameters here. If we do, for example, 8 Gaussian decomposition, we have 8 times 3 parameters along each line of sight. So we developed something to do an efficient initialization of the parameter, which is what we call a multi-resolution process from a coarse grid to a fine grid. Basically, the first step of this algorithm, this initialization, is to minimize, to fit the mean spectrum of the PPV cube. So we can average it spatially and get just an average spectrum. If we want to fit 8 Gaussians, we fit 8 Gaussian on the mean spectrum. So we have a first solution. Then instead of averaging the whole cube, we can decide to average it, to cut it into 4 subcubes and to average it such as we have 4 mean spectra. And we can get the solution we have from the first iteration, from the mean spectrum, to initialize the optimization at this resolution, which is just a 2x2 grid. And from this point, we can really use the full formalism we've seen before, which includes spatial regularization. So we force the solution to be spatially coherent over these four pixels. And then I think you've got the idea. We can do the same, re-subdivide the cube and use the solution we got at the previous step until we reach the native resolution of the observation. So this is going to be more clear in a second, because we are going to visualize this multi-resolution process. So this is again the synthetic observation. On the left here, you have 8 panels, right? Because it's an 8-cushion decomposition. We can visualize the column density on the left, which is just proportional to the amplitude times the velocity dispersion of each cushion, the position, so the velocity centroid of each component, and the velocity dispersion. And we are going to start from the mean spectrum. So mean spectrum, only 8 components, 8 cushions. And we are going to increase the spatial resolution to refine the grid. So at each step, we use the full cost function with the chi-square contribution and the regularization to force the solution to be spatially coherent. You see here that the solution is smooth. And on the top of that, because this is H1, each velocity dispersion map varies around a mean that is reasonable. So that you can call this map, for example, WNM, because it's around 8. This map, this filament here, is around like between 0 and 1, so we can call it 0. So now we can combine this map just based on the mean velocity dispersion of each cushion components, and we can try to build a 3-phase model of this synthetic observation. So what you see here are the 3 column density maps for the WNM, the CNM, and the unstable gas. And we can compare that directly to what we get from the numerical simulation, just by applying 2 cuts in the temperature field. So the difference is not bad, and we can quantify how close we are in terms of a power spectrum. So here you see in cyan and blue the power spectrum of a combination of the CNM, and in red and orange the difference for the power spectrum of a combination of the WNM and the LNM maps. So there is here a potential for studying the 3D density field. We see that we are able to recover because we made those assumptions of spatial smoothness of the solution plus minimizing the variance of the velocity dispersion. We can recover the distribution of the gas in each phase. So we can do the same for the velocity fields, which is even more interesting for us today, because the statistical properties of the velocity field tells us about the statistical properties of the turbulent cascade that is generating the pressure and density perturbations, triggering thermal instability and forming CNM clouds in the simulation. So again, here the difference is really nice, it's even better, and we are able to recover the shape of the power spectrum for the velocity field. So I would like to pause and maybe we can discuss the questions before moving to the applications. So please feel free to ask questions about this this algorithm if you have some now. If not, I can go on and we can discuss this at the end. All right, so we applied this on a real PPV cube. Actually, the PPV cube you saw at the beginning of this presentation, which was an observation around the North Ecliptic Pole. So just to give you an idea of the size of this field, This is 12 by 12 degrees field. So we have something like 150 square degrees, which is a nice volume to probe the statistical properties of each phase. But what we've done here is that we wanted to focus on trying to understand the properties of the warm neutral medium, the warm phase. You can see here the mass fraction maps for each phase, the CNN, the LNM, and the WNM. What's interesting is that it varies. It varies considerably. You can have a CNN mass fraction that is close to 0, so pure WNM along the line side, and sometimes a CNN mass fraction of 30% when you have a cold filament along the line side. But we can still have an idea of the mean properties of this field. About 64% of the mass is in the warm phase, 28% in the lukewarm neutral medium, and only 8% in the cold neutral medium. So these cold H1 filaments are really important because they are the seeds to form molecular clouds. And we know now that they are highly correlated to the magnetic field also in the galaxy. But in terms of mass, at least in this field, it's not really a lot of mass. So as I said, we focused on the warm neutral medium and especially on trying to describe the statistical properties of the velocity centroid of the WNM. It's difficult to analyze the velocity centroid compared to a column density map because this is not just a projection of the 3D underlying velocity field. When you compute the velocity centroid of a PPV cube, what you have in reality is a density weighted quantity. So if you have very dense gas along the line of sight, for example, a CNM cloud, this is going to impact your centroid velocity field. You are going to see only the value at this particular point along the line of sight, and this is going to change the statistics of the underlying velocity field you would like to extract. But here, because we've been able to perform a phase separation, we can just remove the contribution of the CNM, even the contribution of the unstable phase, to be sure that the projection from 3D to 2D is not dominated by these high density fluctuations. So first of all, we can compute the power spectrum of this centroid velocity field. We found a slope of minus 3.3 basically, which is not exactly the value we expect for a subtransonic turbulence. We expect a Kolmogorov-like value, minus 3.6, and we get minus 3.3. So we explain this difference by the fact that when we take only the warm gas, which is 70% of the mass, but there is still 30% of the mass which is not in WNM. When we did that, we removed an important volume from this PPV cube. And removing from something from the PPV cube is going to impact the projection from 2D to 3D in the real space and in your PPV cube observation. And when you remove something, we've tried with synthetic numerical observation, the effect is always that you increase the value of the power spectrum slope, basically. But we are not too far from what we expect. What's interesting to say is that the impact of removing this volume for the velocity centroid is not as important as what you get when you do it on the column density field. So then we can also use this centroid velocity field not just to compute the power spectrum, but to deproject the velocity dispersion of this centroid velocity field. We have a 2D map of velocities, right? So we can compute just the standard deviation of all the values in this field. And we know that this sigma here is a 2D projection of the 3D and underlying velocity field. And that's what we are gonna use to infer the value of the 3D velocity dispersion and to subtract it from the observed velocity dispersion of the mean WNM profile. Because we have a model of a PPV cube for the WNM, but this is still a combination, a quadratic sum of a thermal contribution and a turbulent contribution. So using the information we get from a 2D projected velocity field, we can subtract that from the information we have along the line of sight, along the v-axis of the PPV cube. So by doing that, we were able to extract the thermodynamic properties. We get a temperature of about 6,000 Kelvin, a density less than 1 particle per cubic centimeter, and thermal pressure of about 4,000 Kelvin. So this is exactly what we expect for the warm neutral medium based on all the literature. For example, we can put this value on the pressure density diagram and compare this with the standard model of the thermal equilibrium curve from Wolfire et al. 2003. This is a curve we obtained by taking a chemical network to compare the heating and the cooling that is acting in your fluid in the solar neighborhood. And this curve is important because it tells us where thermal instability can grow. In that regime, thermal instability is able to develop. We can also compare the value we obtained for the WNM with the mean pressure of CNM clouds obtained in the solar neighborhood by Jenkins and Tripp 2011. And the mean pressure is relatively the same. So as we expected, it means that the warm phase and the cold phase are kind of coexisting at pressure equilibrium within a range where the heating and the cooling processes allows thermal instability to develop and to grow. So the standard model and this region where thermal instability can grow. All right, so I'm gonna move to the second part of this seminar, and we are gonna take a look at an H1 observation again, but in the halo of the Milky Way, in the HVC. So HVC stands for High Velocity Cloud, the HVC complex C. It's the more massive cloud in our galactic halo. It's located at about 10 kiloparsecs from us. So the mass is something around like 10 to the 6, 5, 10 to the 6 solar masses. So this is this entire cloud here with the main body that is here. This is an orthographic projection. The main body and what was called in the literature the Q of the complex. And we are going to try to decompose a very, very small part of this complex. It's less than 1% of the mass of this entire complex, but still it's something that is around maybe 2,000 or 3,000 solar masses. So we have a one arc-minute observation of this small region of complex C. You can already see here that the location of this field is at an H between the complex C and what we can't see in H1. But what we can't see in H1 is obviously something. It's gas that is ionized, either warm or very hot gas from the galactic halo. So this one arc-minute observation is great because it allows us to cover a very large range of scales. You can see here the scale 50 parsecs And basically we cover a range from three-ish parsecs to 300 parsecs. So this is interesting because we'd like to probe the properties of H1 in the galactic halo, also because it tells us something about its surrounding medium. But it's also a very unique laboratory to probe the phase transition in general, the thermal condensation of the gas, because we can see scales that we just can't see in the Milky Way disk because we are inside. So applying ROHSA, again, we were able to separate these fields into two environments. On the left, you have something that is more related to the edge of the complex, where we only see warm and unstable gas. Here, the color code is blue for the WNM, green for the unstable gas, and red for the CNM. So we only have WNM and unstable gas along the edge, but along this, what we call finger-like structure or this protrusion, we really observe the formation of cold H1 filaments that you can see in red here. And this protrusion, interestingly, is perpendicular to the edge of the complex C. So again, we can look at the mass here. Similarly to what we find in the solar neighborhood, surprisingly or not, I don't know. We have only 7 or 8% of the mass that is in the cold phase. So for this study, I would like to show you one plot, which is the mass size relationship. The color code we used here is the same: blue for the WNM, red for the CNM, and green for the NM. And this plot is really nice because it allows us to see where, in terms of spatial scale, this transition occurs. And we find something around 20%. So we call that the cooling length. It's the length where thermal instability grows, and you are able to go from the warm phase to the unstable phase. So using the sun speed of the gas in that region, we can infer a cooling time, which is of about 2 million years. And the question we are used to ask to understand, to see if we understand the theory behind thermal instability, if thermal instability is really responsible for that, is the following: is the cooling time lower than the dynamical time? So for the dynamical time, we took the mean thermal crossing time of the WNM clouds, and we find something around 3 million years. So the reason why we ask this question is because if it is not satisfied, if the cooling time is not lower than the dynamical time, the energy that you lose by radiation is too small compared to the increase of the internal energy due to this perturbation. And the process is just considered as an adiabatic process. You don't have enough time, or you don't cool efficiently enough to be able to condense the gas, and the condensation mode of thermal instability cannot grow free. It's kind of inhibited. All right, so we've performed a phase separation in the Milky Way disk in the HVC complex C. The last thing I would like to show you is not phase separation, but still a Gaussian decomposition using ROHSA in a nearby galaxy, NGC 4214. This is very preliminary, but I think it might be very interesting for you to see that. So this is an H1 observation from the THINGS survey. I'm sure you're very familiar with this survey that was published in 2008 by Walter et al. This is a dwarf galaxy, barred irregular galaxy, and it's located at about 2.9 megaparsecs. When we do a Gaussian decomposition, especially current decomposition of this field, we find that we can well describe the signal with only 4 Gaussians. 2 of them are more centered on the bulk of the whole emission in the PPV cube. These orange Gaussians are narrower compared to the 2 broad Gaussians we see here. So I don't want to say that it's CNN because we don't have the spatial resolution with when you have only when you have 80 parsec within 1 pixel, you don't have the spatial resolution to really resolve correctly what's happening in that parcel of gas. So we're not talking about WNM and CNN here, but it's still good to have this tool, this way to model the signal to see if there is a difference in this PPV cube. So I'm gonna call that like broad wings and narrow emission in the center. So we can look at the spatial distribution of this emission. First, we can look at the velocity field. Here on the left, it's the velocity field, centroid velocity field associated to the narrow components. So we have a very nice rotation, as we can expect, especially because this galaxy is not face-on galaxy. It's you have a certain inclination, and a similar velocity field for the broad wings, even if the axis of this rotation map is not necessarily the same. So when we see that, first we could say, okay, this is all due to rotation. Okay, we have a galaxy that is not face down, so we have dynamic in the PV cube that is maybe purely due to rotation. But it becomes really interesting when we look at the spatial distribution of these 2 components. On the right, the broad wings is more centered. The spatial extension of the wings is nothing compared to the spatial extension of the narrow components. And we can see the bar basically only in the orange component here. So I thought it was kind of interesting and intriguing to see that we can separate the emission of this galaxy into 2 parts. The spatial extension is definitely not the same. And when you compare this with some other observations, here on the right you can see the far UV emission from galaxy, which traces not all but parts of the star formation in the galaxy. We see that the spatial extension of the broad wings we modeled in this PPV cube of H1 is similar to what's to the star formation traced by the far UV galaxy. I can show you the 2 superimposed. So here on the right, the broad wings with the far UV galaxy, and on the left, the narrow component with the far UV galaxy. And the narrow component is even more interesting if we take a closer look, because it seems that at some locations, galaxy fills holes in this narrow H1 component. So I don't know. I'm still trying to figure out what's happening here, but it looks like this spatially extended component described by the 2 narrow components in the center of the PPV cube is maybe more associated to the disk, and what we see with the broad wings that is correlated to the distribution of the star formation is either gas that is at the disk halo interface associated to the galactic fountain process that has been just launched by the activity, this star formation, or just still within the disk but with a velocity dispersion and that is different from the rest of the gas, or a differential rotation. I don't know. This is something I'm trying to figure out these days. But I guess my take-home message for you today here is that so this is just a screenshot of the star formation laws and threshold that I'm sure you're very familiar with from the Leroy et al. Paper 2008. It seems to me that it could be crucial to push forward the way we analyze H1 ppv3 to fully understand what's in this ppv3, because they always impact every star formation law and threshold, especially the velocity dispersion of the gas or the rotation curve that is very often extracted from H1 observations. So I think I'm gonna think about that more in the next few months, and I do think there is a road to analyze this data set using this ROHSA algorithm. So yeah, I think my last slide is going to be this amazing picture of the Pink survey. I really like to see this amazing data set. The galaxy I've analyzed just this little guy here, but we have a lot of galaxies in this survey, and it's going to be even more. We are going to have more galaxies in the future with the SKA, and it's going to be very exciting. So thank you, and I will be very happy to answer your questions.
Thank you, Antoine.
So maybe I can just stop sharing my screen and answer your question.
So, yes, Norma.
Hello, thank you for this interesting, very interesting talk. So I have say two questions. First, the result you showed for the complex, I found very interesting. The transition you find from the to the cold, which is the mass fraction is very, very small compared to the other phases, to the cold, neutral, medium phase. This transition, how do you explain by, I mean, is a phase transition, is and the length and what you call said the cooling length, this 20 megaparsec, is attached just to this complex, or you can think in terms to apply to other complex and then to find some kind of common mechanism, or just some said common cooling lengths. I found I mean, my message is also to try to understand deeper this part. I mean, this is one part of the question. So if you like to answer, and I have another question. Thank you.
Sure, thank you very much. So why do we observe transition in this part? I believe it's closely related to the fact that this is located at the edge of the complex. So it's probably the interaction between the complexity and the surrounding halo that allows the phase transition to occur.
Yes. Do you have some mechanism? I mean, some said equation to, I mean, some dynamics, because to visualize that. I mean, I understand. Yes. But
Yeah. So one mechanism could be because the morphology is very specific. It's a finger-like structure coming out of the edge, right? And actually, we can't really see it clearly in this figure, but we observe several of them along the edge. So one hypothesis could be, and as you said, we have to explain how it could be an interaction between the edge and the halo, and this interaction could be an
yes,
HD instability, like Rayleigh Taylor or Kelvin Helmholtz. We don't really know how the cloud is moving, so we don't really know if it's more Kelvin Helmholtz or Rayleigh Taylor. But I think it's definitely an instability.
yes.
Right.
We have a question by Caroline.
Yes. Hello, Antoine. Thank you for this very interesting talk. I had a question on your Galaxy application. You deduced before that your critical length was at 20 parsec. And so I would have expected that you can only apply the ROHSA method to, or decomposition to galaxies where you can resolve these 20 parsec scale lengths. So I'm guessing the galaxy you presented is further away than this. And so how do you understand what you get, and why, what do you expect differently to be happening for a closer galaxy where you can indeed resolve these smaller scales?
Right. Thank you. Thanks for that question. That's interesting. I actually don't think because of what you just said, because it's too far. We don't have the spatial resolution. I don't think we can call these components CNM or WNM. We can't really tell what's the temperature of the gas because of the beam smearing. The beam smearing is too important. But it's still useful, even if we can't really say what's the phase. The fact that we see a significant difference of width between the wings and the bulk of the emission and the spatial distribution can probably tell us something about more the dynamics of the gas than the thermal properties of the gas. But if we find a galaxy that is closer, as you said, and we have, I think it's really challenging because so the cooling length in this HVC was like 20 parsec. So as you said, we would have to be able to resolve this scale to really not be being dominated by this beam smearing effect and to say something about the temperature of the gas. So I think for these galaxies, ROHSA should be seen as more like as a spatially coherent Gaussian decomposition, not specifically a phase separation algorithm.
Thank you. To follow up on that, so if you had observation that resolves this 20 parsec, like that, where you can study the different phases in other galaxies, do you, like with, I don't know, with ALMA or for the Magellan Cloud, if the resolution is coarser, do you expect that you will that you would have a different equilibrium between the phases depending on galaxies, or is this something that is supposed to be universal?
No, we definitely expect some differences, just because thermal instability can develop under specific conditions. One of them is linked to the equilibrium there is between heating and cooling in the gas. That what makes your S curve in the pressure density diagram. And this S curve is going to change. In a low metallicity environment, you have less metals, so you can cool less efficiently. It depends what's the 5D radiation field, of course. But I don't think this is universal. Definitely not. But I mean that would be very interesting to just try to see it empirically. The cooling length is also related through thermal instability to this question. So if the cooling length is different, it might be because the heating and the cooling processes are different.
Thank you.
Any more questions? I have several questions, but is anyone else?
I think Norma had a second question.
Second point, I think.
Yes.
Thank you. Thank you. Yes. In the meantime, I want to add. I mean, because what you just said before. Yes, I think. I mean, that clarified my previous question too. So I think the cooling length could be could stay for the different cloud, for the different complex and cloud, could stay in some range, but in my view, we should expect that will be different because, as you said, there are and also that it should depend also of the size on the mass. I mean, because this is this is in the edge. I mean, is assuming because of the interaction with the other part. So that really, I mean, it's a very interesting again a point to better quantify and visualize. The other question I have is concerning the algorithm ROHSA. Is this completely new, or there are other? Because I don't work with this algorithm, as you know. Is other a similar algorithm from which you have, I mean, improved, or is something which is really, I mean, which is completely original, completely new? In connection with that, I saw that you add some terms which are convolution or wedge, and you explain it in terms of the image and so on. But this, I assume, you introduce some input or some I mean, some assumption. I mean, I would like to know if you could said something. Thank you.
Sure. Of course, there are many Gaussian decomposition algorithms, but they are all trying to find a smart way to initialize the parameters of the decomposition and to do an iterative process to be able to have a spatially coherent solution. The novelty of our algorithm is that we asked for that mathematically and specifically in the cost function. It's not we didn't find a way to smartly initialize the decomposition to have a spatial coherency between line of sight. It's included mathematically in the cost function. You can really tune the strength of this regularization, this spatial regularization, with the hyperparameters of the algorithm. Something you can't really do if you just initialize it without asking for it specifically in the cost function. So we haven't developed anything for the optimization. The optimization, the gradient descent of the algorithm is kind of a black box for us. Our work was really to design, as you said, these new terms in the cost function. Is really the novelty of this algorithm to go beyond the chi-square basically in how we initialize the chi-square contribution.
And for instance, sorry, I don't want to, if there are other questions, just to see. Do you expect, if you expect, for instance, if you have the pictures, I mean, I am thinking in general terms, if you would like to take into account or to introduce also non-Gaussianity, this will need, I mean, because it's very attached to Gaussian, but I am imagining that it could also, I mean, in terms for people working with non-Gaussianic statistics, it could be also a way to, yes, I understood. I mean, I think, do you?
Yeah, that's a good question. We thought about that. So we could decide to go beyond the Gaussian model with some more complicated functions, which is not really this is something we could do because regularization is just something you apply on the parameters, right? So the model is independent of the regularization here. So that's one option. And the other extreme option for maybe what you mean by non-Gaussianity, and I haven't talked about that, but recently someone named Claire Murray has used a deep neural network to do the same job.
Oh yeah.
The CNM mass fraction from observation. So we are far from the Gaussian modeling. We don't even know what's the function behind the deep neural network. It seems to do a very good job.
Thanks.
Thank you.
We could discuss, I mean, in later,
Sure.
Another day. Or,
I would be very happy.
where are you? Where are you? I mean, in.
I'm in Canada, but we can Zoom.
Yes, by electronic mail. Thank you.
Thank you. You
Antoine,
had questions?
Yes, I have a question for you. When you decompose in Gaussian, you decompose in, I'm not sure I understood well the way the decomposition is done to separate the warm and the cold medium. I think it's related to the penalty function that you put. No, is it correct? Well, anyway, well, my question is, do you decompose in any kind of Gaussian and 2D functions? I mean, do you see? Well, my question is the following: Can you recover something like the Larson laws in your medium if you have the velocity dispersion, the statistics of the velocity dispersion, and the size of the objects?
We've done that for the HVC complex C actually. Yeah, once you've done the phase separation, what you assume basically is that within each phase for the WNM or the CNM, you still have a quadratic sum, a mixture of turbulence and thermal contribution. So what I call WNM, we've put a prior on what's the WNM, but it's still a contribution from the thermal and the turbulent contribution. So then you can cluster the CNM phase, for example, and look for the properties of the clouds, like the mass size relation or the velocity dispersion size relation. Definitely. Mm-hmm.
And did you compare to CO maps like the day-metal survey?
No, not yet. Not yet.
Because
you mean for the
you should do the
galaxy?
dense gas. Well, if you do the CO map.
Yeah, that's something that I hope I want to do someday. It's once you have seen the maps, naturally what you want to do is to compare that with CO maps. Yeah.
And this is available. I mean, this is the data
for
available for the cube with the CO.
For the galaxy, you mean?
Yes.
NGC? Yeah.
No, for the
No,
Milky Way. For the Milky Way.
For the Milky Way. Well, the difficulty in the so what we do in the Milky Way is usually at high latitude because we want to avoid self-absorption effect for each one. So it's very hard to, well, first you not always observe CO. And if you observe CO, it's really hard to say if it's associated to this gas, this cloud. And in the disk, the self-absorption is so strong and the ambiguity of the rotation is so strong that it's hard to do the association H1CO.
I think it goes to high latitude, like 30 maybe. Well, it's not very high, but maybe you can spot some.
Yeah, maybe. Yeah, in a very specific region, it would be interesting. Yeah.
Okay. Thank you. I have more questions. I will ask you later.
Yeah, sounds good. Thanks very much for inviting me.
Thank you very much, Antoine. So thank you, everybody, and see you for the next seminar. Thank you.
Merci,
Great
Antoine.
day. Merci.
Salut.